For the first talk for the day. It's my pleasure to welcome Tom, chair of the SYCL working group, who's going to give an update on the SYCL State of the Union. Take it away.
Thanks, Axel. So, morning, everybody. So hi, for those of you who don't know me, I'm Tom Deakin. I'm a senior lecturer at the University of Bristol, but also I have a very privileged role to be the SYCL working group chair for Chronos. We are whilst I have a little bit of time, I wanted to share what happened at the hackathon earlier this week for those of you that weren't here for that. So the hackathon this year was supported by the Chronos working groups with the SYCL working group, and we had some great mentors made up of member organizations from the working group itself. And the goal of this hackathon was to try to support people that are writing SYCL applications that have something that they wish to work on, and to give them sort of access to these kind of SYCL experts that help us in the working group to find the standard, but have all this amazing SYCL knowledge to try and kind of get that knowledge into the hands of users and share all the best practices and help them get unstuck with some of the kind of complicated challenges that they are working on. We also had a series of presentations from some of those mentors as well, sharing how to get started with porting CUDA AI applications to SYCL, how to get started with SYCL to begin with, how best practices for using the two primary implementations we have, Adaptive CPP and DPC++, with all of the kind of tools and plugins and libraries you need to get started to really get SYCL code running absolutely everywhere. And so that was the goal of the hackathon, to kind of share all those top tips and best practices, and also give people the support they need to develop their projects. So we had 4 projects being worked on, and kind of some highlights just from 3 of them here. One of the people, they're in this room now, so you can go and find them, see if you can find them in the coffee break and identify these people. But someone was working on getting Adaptive CPP with the JIT compiler working in a local install of Compiler Explorer. This is really cool. So you'll see in a moment in a slide that on SYCL.tech, we integrate with Compiler Explorer, so you can try SYCL in the browser, but only currently works with Adaptive CPP. With DPC++, but getting it to work with Adaptive CPP as well is going to be really cool. So hopefully we can take a lot of that work forward and get that either upstreamed into Compiler Explorer itself, but also integrate that with our kind of ecosystem for people to try SYCL in the browser. So that was really awesome to see that happen. Some challenges with JIT, right? How do you get JIT without, so you have to run the code, but it was really cool to see that happening. Then there was some really interesting kind of science happening with trying to do some interesting computation around the intersection of cubes with spheres. So you've got all these kind of bubbles of spheres in like a molecule, atoms in a molecule, and you need to find some intersections of sort of cubes. Some interesting parallel challenges there, and hopefully they're able to make some progress. And then some really cool stuff with people wanting to write Python code and program SYCL from Python. Obviously in OpenCL, you can do this with PyOpenCL, right? It's all nicely integrated. But with SYCL, they were interested in automatically generating SYCL kernels and then using some of the extensions to SYCL through one API to make that a lot easier for them. Some of those extensions we're already thinking about in the working group. Some are things for us to think about in the future. And you'll start to see some talks actually later in the program today around some of these, this idea of being able to generate SYCL kernels and ingest them in your SYCL program rather than just, have to write C++ and compile it all upfront ahead of time. So that was the hackathon. It was a really, really great, and it was, it was great that there were so many working group members there to be able to support. So thank you to the mentors for that. From the working group has been busy over 2025. So I was looking back at IWOCL 2024, and since then we've been doing a lot of work. Our priorities, though, in that last year is to try to standardize and implement through our members improvements and features to SYCL to address real world problems that users really have. Kind of rough edges with SYCL as an API, maybe things that are missing, things that are slow, things that don't give them the performance they need, and try and tackle those kind of high priority challenges for them through delivering new APIs and extensions. And we've been working carefully through this. We've been designing the extensions. Many of them have come from vendor extensions, so many people have already tried them out for real at least once. Working on standardizing those, but also making sure that we have the tests in place and also that an implementation is in place as well, so that when the extension is eventually shipped, it's kind of ready to go. People can try it and it forms part of an extended part of SYCL. Kronos has the mechanisms of these extensions. Ben did a fantastic job of explaining how extensions fit into the Kronos ecosystem yesterday. And really SYCL is following a very similar idea where we extend the standard through new APIs. This gives us time to make sure that they are exactly defined correctly. Once things go in the standard, it's really hard to undo things. It takes a long time to do that. So we've got to be sure it's right. We've got to be sure it's designed correctly to solve all the problems that people are coming to us to ask us to solve. We have one KHR already ratified, so gone through the Kronos board and is ready. It's called Default Context Query. It's not like the most exciting KHR. It just allows you to query whether there is one true single context in your SYCL application. But that can be really useful, especially people coming from either CUDA codes, where this basically is the kind of the default context in CUDA, but also with some patterns from the SYCL-O-Matic tool. So people coming from CUDA automatically translating 90% of their application with a tool to SYCL. And there were some patterns in there that meant that making sure we had a default context was a really important performance improvement to be had. So that's there, that's done. The other ones here are really close or nearly close. We've got some new kernel submission APIs. So rather than doing q.submit, we've got some new alternatives to that to make it feel more C++-like and help reduce the submission latency for when you have lots and lots of small kernels, for example. So that's in the works. That's nearly done. We've got a design and some implementations and some tests on the way. As I said, the default queue construction we've dealt with already, and then things like more reduced precision data types and complex numbers is in the works as well. Most of these extensions, many people have seen before. They're coming from industry. They're also coming from previous presentations at IWOCL. So many of the vendors present their work at IWOCL and kind of show you the extensions that they're doing. So many of the stuff that's coming is stuff that you've already known about. So if there's something you've seen that is really important to you, please let us know and we can help prioritize the work on it. The other thing that's happened since IWOCL last year is that the development of the specification, so our draft version of the specification is now done completely open source in the public. So if you go to the Kronos GitHub page, you can find the latest draft version of the spec that's kind of running ahead of the released version, where many of these draft KHRs are there as pull requests. So you can check them out, see if the API is what you're after, and give us feedback on that directly on the issue. So yeah, you can read more about some of the motivation for that in the blog post that we released back in November at the URL there. But it's really exciting to be able to kind of share this open development of the parallel programming model with yeah, as things are going. But it's all on the Kronos group GitHub page, so you can find all of that stuff there. With IWOCL, we target a new release of SYCL. So we have, I think, at the very beginning of the week or very late last week, released revision 10 of SYCL 2020. As with all revisions, they're kind of minor updates that just provide mostly clarifications and fixes and things. But SYCL 2020 revision 10 is now released. So if you have downloaded a copy of the PDF, please make sure you grab a new one with revision 10. It's available in the registry. If you render the HTML, it's all the new Rev 10 stuff that is there now. The main thing to kind of highlight is we have a new appendix, Appendix F. These are those optional extensions, those KHR extensions that now is the home of where they all live. So we have one, this SYCL KHR default context. It just gives you a query to check that if the context you get back, say when you create a queue without any arguments, is always the one true single context. So it's cheap to create many, many queues. That's a pattern that we saw happening in SYCL-O-Matic. So this query gives you a way to kind of confirm that that is what is happening. Many implementations, some of the implementations do that anyway, but this is just a way of querying it to make sure that it's there. Other kind of highlights to go through is if you use SYCL.vec, we made quite a few changes and clarifications and fixes to SYCL.vec. The way that SYCL.vec was specified was essentially not implementable in the PDF and the PDF of the standards. So we have resolved that so that it is implementable. There are all sorts of challenges with conversion of what do you do with a scalar to a vector type or a vector type to a scalar, and how do you do the arithmetic of all these things, the swizzles. There was a lot of complexity in there in terms of actually how it all works and how C++ handles all of those types. So that's all been clarified now. So do go and check that out. If you've been using SYCL.vec, it shouldn't actually mean any changes to your applications, because implementations did basically an implementation of SYCL.vec, but the standard is kind of caught up to make sure it matches what is implementable. We also clarified the behavior of SYCL-free. SYCL-free is the deallocation of unified shared memory. There were some overloads where you give it a queue, and it wasn't clear in the way the standard was worded exactly what the behavior should be. It's not submitting a free to a queue, so it's not like the CUDA enqueue release of a memory object. A SYCL-free is more like a deallocation, and may or may not be blocking. You can't rely on its synchronization behavior in your application. So nothing is, again, it's just a clarification of wording. Nothing's really changed, but it clarifies exactly what should happen with SYCL-free. A nice change is we updated the introduction to the actual specification itself. So SYCL has this introduction. We call it what is SYCL. So there's been some simplification to that to kind of make it more straightforward to explain to everybody what SYCL is in terms of what does the API do, what it's there for, and the motivation for its behavior. SYCL was originally kind of conceived out of a subgroup of OpenCL and then grew into its own working group, and we've had several releases of SYCL. And so in some of that, we relied on OpenCL definition, so much so that we just deferred to OpenCL and said, this is what it is in OpenCL. And so we're still fixing up some of those things, the first of which is device types. So we've now defined what a CPU is properly and a GPU is, and all of those kind of different types of devices. It was slightly unclear in the spec, but that is on its way. That's in revision 10. So we've defined those things now. I've talked about the default context behavior. Yeah, this was where SYCL-O-Matic would create a brand new queue for every kernel submission and then throw the queue away. It's a pattern that SYCL-O-Matic had. So you make a queue, you submit a kernel to it, you throw the queue away, and everything is fine. The kernel continues running in the background. But that can have a performance impact if the kind of the context that lives behind that queue has to be recreated brand new every time. So we've changed some of the behavior to say that if you do that, then you do really just get this one singular context that lives, the default context in the background. That's a big performance improvement for those kind of codes. We have the SYCL language macro. We've now defined exactly what that macro, the number is, and what it means for the future proofers as we start to develop SYCL next. So as well as developing these KHR extensions, we're thinking about a path to what will be the next major release of SYCL at some point in the near future. So we've redefined what SYCL language version means for 2020 so that we can then make it make sense going forward. Those of you that read the specification very closely would have noticed that hierarchical parallelism in SYCL 2020 is a feature that came through from 1.2 and 1.121. Had this kind of note that was somewhat ambiguous that said, well, this is very difficult to implement, it's problematic, it's likely to change in the future. And we have now clarified that in revision 10 to say, well, actually, what we meant to say is deprecated, which is a more kind of formal term within the specification. So we're still working on future designs for what a replacement for hierarchical parallelism could be. But we found that for modern devices, the current way hierarchical parallelism is specified just doesn't give people the performance, isn't fit for the purpose that it was intended for. So more designs to come. We're still figuring out what the replacement exactly needs to be, but it's clarified that is deprecated. Something else that's interesting is people do a lot of cool C++ with SYCL, and they often use SYCL as the fallback for C++ when they can't do everything they need in pure C++. Then they need to use SYCL for the heterogeneous programs. Okay, and then C++ provides this constant expressions, and we have kind of reduced the restrictions in device code. So things like recursion, things like that, do not apply to constant expressions because they can be evaluated at compile time. So although maybe a GPU can't support all of the kind of C++ features that would be there, then it's still totally fine if it's in a constant expression. So things like long double, for example, might not be supported on all GPUs because it's in a constant expression. The compiler can deal with it, so it's all totally fine. So it just kind of slightly reduces those device code restrictions to make it much more aligned with kind of typical C++ styles of writing with things like constant expressions. So yeah, that's the main highlights for revision 10. Because the spec is all developed on GitHub, you can go and look at the release notes and see all of the pull requests that have been merged in since revision 9. If you really want the kind of fine-grained detail of exactly what lines of the spec have changed, but the kind of fully rendered version of the spec is in the registry. So make sure you go and grab a copy of that. SYCL.tech has had a huge facelift. If you've not visited it recently, SYCL.tech is a community page that's moderated by CodePlay software and contains a lot of great ecosystem knowledge around SYCL. And there's lots of links to people using SYCL, projects that are using SYCL, SYCL events that are happening in the calendar, news and that kind of thing. But also new, released earlier last year, is the playground for SYCL.tech. So this is where you could try SYCL directly in the browser. It uses the compiler explorer that I mentioned earlier. And you can see here that this is a simple, I think it's vector add that I'm showing here. So this is some SYCL code an example on the left-hand side, just for vector addition. It shows you using the output from the DPC++, Intel's DPC++ compiler. It shows you the assembly of the program, but also you can run the code as well and see the output as well. So this is a great way to get started if you just want to play around with SYCL or try it out, or uses the DPC++ compiler. But it was great with the hackathon earlier today that there's seems to be a good path for supporting adaptive CPP in there as well, which is on our roadmap to enable that to happen. So whilst the specification is the source of truth for how SYCL should behave, just as in C++, the C++ specification is the source of truth for how C++ should behave. A specification has to solve many roles, and Chronos specifications in general are very human readable. They're written by humans, written for humans to read and ingest and understand what's going on, and that includes both implementers and users. Like all of the Chronos specs are very easy to read relative to other specifications. However, a C++ community often expects this more CPP reference style way of understanding. Just tell me what the APIs are rather than a full list of or the full behavior. I just need the functional signatures. So we have a CPP reference inspired reference guide for SYCL. It's available here at chronos.org/SYCL/reference, and it contains all of the APIs in SYCL 2020 with a short description of what they happen, much more kind of ingestible than the large spec document. This can be useful for just needing to find specific APIs for the SYCL specification. So like a handy developer resource that kind of complements the spec as well. So if you've not seen that, do check that out too. So implementation update. One thing that's really cool to see with SYCL is lots of people are trying to implement SYCL, and there's always been a very healthy research compiler and research implementation kind of ecosystem around SYCL, with people trying to implement it in all very different ways. Here is just then kind of a highlight of the most mature, the most feature complete of those compilers. First up, we've got the Intel's OneAPI PC++ compiler. This is the SYCL 2020 conformant compiler, conformant for CPUs and GPUs from Intel. But it does support, it's developed in the open source, so you could download it and you can compile it, and it supports any CPU that LLVM supports. And then CodePlay Software provide their OneAPI binary plugins that you can then use to use DPC++ to target NVIDIA and AMD GPUs as well. So that's the first kind of performant compiler. For those that don't know, conformance means that Intel has submitted to Khronos a kind of confirmation that their implementation correctly implements all of the SYCL specification according to the conformance test suite that the working group has also defined. So it's kind of one of the really lovely things about these open standards is you have this test suite. So these conformant implementations do give you this guarantee that everything is going to be fine on the platforms that they promise it works for. So that's our conformant implementation. But then we also have many others. Adaptive CPP, as you know, implements basically all of SYCL 2020 at this point, with a few minor exceptions. This is driven by Axel here. And based again on LLVM, supporting CPUs, Intel, AMD, NVIDIA GPUs, again, huge coverage of the different devices. And this is really cool, right? So if you have any one particular device that you're targeting, you now have choices of compiler of which things to try, which is typical of what we'd expect from most parallel programming languages. If someone only gave you a single C compiler, you'd get a bit nervous about whether that C compiler was correct and going to work for my platform. But having this kind of choice of compilers we can use is a sign of that really healthy ecosystem. I've mentioned LLVM a lot, and kind of missing from this slide, but you'll have seen a lot of work happening in the background with RFC's request for comments in the LLVM source directly, where Intel and others are working to contribute a lot of the SYCL implementation up to LLVM directly itself. So at some point in the future, hopefully we will see SYCL supported like natively within LLVM, just like all the other programming models too. So that's some cool stuff. Other implementations, things like CDAC. This is one of the national labs from India. They have the Para-S compiler. This supports SYCL on x86 and IBM CPUs and ARM CPUs and also NVIDIA GPUs. It's free to download. You can just go download it. It's not open source, but is a free compiler. Then there is other kind of interesting implementations, things like SymSYCL. This was presented at IWOCL last year. This is a SYCL for kind of debugging and verification, single-threaded library-only implementation. Recently, SymSYCL has integrated with some of our CTS CI in the Khronos page, so that we're now sort of automatically running the CTS. When we develop new CTS tests, make changes to the CTS, we're kind of checking them against SymSYCL too, so that we can make sure that all the implementations our CTS is correctly implemented against the implementations and are correct. TriCycle is a long-standing one of our research implementations, supports all sort of things. Originally started by Renan Keriel, lots of FPGA support, but is been pushing the boundaries in how SYCL can be implemented with all sorts of different approaches. And Celerity kind of extends the SYCL abstractions, not just to heterogeneous systems, but distributed systems as well. Extends some of the abstractions there to basically sit on top of an MPI cluster. So you can program GPUs that are distributed too. And then NeoSYCL for supporting some of the NEC devices. I know there's some weather centers in Germany in particular that have these SX Aurora cards, and this NeoSYCL is a compiler that supports those. So this is really cool to see all these different implementations targeting both the same and different kind of devices. Just a quick highlight from the UXL Foundation. So Kronos has an agreement with the UXL Foundation, a working agreement framework. And what UXL provides is it extends the parallel programming model with all the stuff that you need to make it practical. The programming model alone is not enough to get real work done. You need the programming model plus all the libraries and infrastructure and tools around that. And UXL is, as their mission, is to try to kind of flesh out this open, heterogeneous cross-vendor programming model that SYCL provides with all of the libraries that you need. Things like AI primitives, things like communication primitives, and all the math libraries that you might need as well. This is all built from open source. At the moment, they're using the DPC++ compiler, but through that, then they can target all of the different devices too. So they define the specification, but also have open source implementations of the libraries too. Part of this UXL Foundation is the One API construction kit. This is something that was mentioned during the hackathon too. And what this does is it lowers the barrier for entry for people with new hardware to support SYCL. The One API construction kit here is shown targeting RISC-V accelerators. And I know we have a poster on this, which in fact uses the One API construction kit. So if you've not seen that, do go and see that too. But it allows you to basically hook into the DPC++ and adaptive CPP runtimes through the One API construction kit, and you just bring in the kind of the low-level parts that you need to talk to your device, and greatly accelerates the path that it would take for a new hardware platform to adopt SYCL, which I think is really cool. Just a couple of minor things then at the end to say, just to highlight, if you would like to learn SYCL and you are teaching SYCL, then the book, Ben is an author of that. Many other Intel colleagues wrote that book. It's a fantastic book. It is free to download as a PDF, but they would of course also appreciate if you bought physical copies. It's a really well put together book. There's a second edition that was released 18 months ago, I think now, maybe a bit longer. That's the edition that you want. So make sure you grab the second edition. It's got the big orange SYCL logo on the front. That's how you can tell. It's a fantastic book. Come to tutorials, come to hackathons, use SYCL Academy. It's had a recent facelift recently. So do check that out. It's on, you can get it from here or sycl.tech. There's the SYCL reference that I mentioned about, and do think about reading the specification. It is a very readable thing to do. And if you need help, there's lots of ways to get in touch with us. If you want to give us feedback, either through GitHub directly on issues, but also the Kronos forum, Stack Overflow we monitor through sycl.tech. Kronos has a Discord as well, so you can join the community to talk about SYCL there. And of course, ask your implementer, tell them your bugs, tell them stuff that doesn't work. Finally, if you'd like to get involved, of course, we are more than welcome to welcome you into the working group. It's great to have lots of a diversity of people that are interested in SYCL joining the working group. So if you're interested in becoming a Kronos member, fully paid up registered member of Kronos, and there are several membership tiers available depending on your type of organization. So please do come and talk to us about that. That's really where all the decision making happens around how SYCL is defined. You are also welcome, of course, to join the SYCL advisory panel. This is no cost. You just have to fold within the NDA that Kronos has around the specifications, and you can join as an invited expert to help us give us feedback on the specification. But you can do this too directly through the GitHub as we develop it open, but we may have more sensitive conversations with our advisory panel members too. With that, I'll finish. Thank you very much, and happy to take any questions if we've got a couple of minutes for time.
Yeah, so I wanted to ask in the context, for example, of Ben's presentation on OpenCL last day. He was saying that OpenCL have approach of integrating used and widespread extensions into a standard. You seems to be briefly touched with SYCL, but could you explain, is it a thing, how you collect feedback on extensions, how you upstream them into a standard?
Sure. So yeah, that's a great question. So I guess SYCL 2020 standardized a lot of stuff in the core spec, and we are now kind of dealing with a new model for how we engage with it using extensions, so that we don't have a big explosion of all these new features to implement again. So we are early in the kind of the life cycle of that OpenCL has of making extensions and then thinking about integrating them. We will integrate those extensions that are kind of well adopted and the other ones that need to be part of the core spec in the future, but we haven't worked out the mechanism and the time at which we need to decide how mature is something to bring it into the main spec, because we're just not there yet. The extensions are all new for the first time.
Okay, thank you.